So, today we are going to discuss one of the major integral theorems called the Stokes theorems. And as I told you, here I have written down the form of the Stokes theorem. It says curl of f dot ds, ds is the surface area vector, double integral over that, the surface integral basically, the surface integral is now related to the line integral. So, the surface has a boundary and on which if you take the line integral it is same as the surface integral of the curl. Of course, this symbol curl I have not mentioned explicitly, though I have used it yesterday. If you remember in the last lecture we have spoken about in the domain, in the 2-dimensional domain D, we have spoken about an alternative form, a vector form of the Green's theorem. So, vector form of Green's theorem so here it was shown that Green's theorem can be written also explicitly like this. I have told you what a cross product between two vectors is, and I have left it to your imagination to know what curl is, because you would know what del is and what f is. But today I am going to do it in a more formal way. Okay, if you want to put f here as vector. Now, this is the vector form of Green's theorem. So, now my question is what is the curl of f? So, let us first learn what is curl of f. That is the question I have also written down here. What is that is the question. Now, let us understand this vector f has three components, f1 I vector, f2 j vector, f3 k vector, and each of those fi's, I is running from 1 to 3, is a function from R3 to R, that is a function of x, y, z. And this operator, nabla operator or the del operator, is given as del x. It is an operator, it is not a kind of real vector, please understand that. Del y, these are not vectors, vectors means these are all numerical quantities, but del x, del x or del y are not numerical quantities, they are operations. Now, how do I define curl of f? Now, to define curl of f, I think this del as if it is a numerical quantity, as a del x, del y, del z as a numerical quantity, and del is truly a kind of vector in R3, and then curl of f is just written as if we are writing a cross product with these two vectors. But in the definition of a curl, when I write cross product of two vectors, you know how to write a cross product, I j k. So, you find the determinant of these I j k. Now, when you write even a cross product, you know that these are actually vectors, right? And so, basically this is also a vector, it is a determinant, but it gives out a vector. Usually determinant gives out a number, but here the determinant gives out a vector. You would be wondering why it is so, but we define it. It is really not a determinant, but we actually work on it as if it is a determinant, as if I, j, k were also numbers. So its operations, the way you expand it, you expand it exactly in the way you do a normal determinant. Del del x, del del y, del del z, and f1, f1, f2 and f3. So, this is the meaning of the curl, and this can be now expanded as something into I vector. What is that something I vector into? So, this part and this column and this row goes this minus this. So, del as if you are multiplying these two, but ultimately it is an operation. So, we define it as del f3 del y minus del f2 del z I vector minus, now just like the determinant, this into this into this, del f3 into del x minus del f1 into del z, del z of f1 j vector plus, now remaining is this because you take out this column, the last column and the first row. So, it is del x of f2 vector f2 minus del y of f1 into k vector. So, if you expand it, this is exactly the expression of the determinant. This is what we mean by the determinant, by the curl, sorry, not determinant, by the curl. So, this is the meaning of a curl. The curl is a vector which is given like this. It is a kind of cyclical thing, 3 2, 3 1, 2 1, y z, x z, x y, right. So, that is the kind of thing that we have here. Now, once I know what is curl of f, I would now like to write down, show what is the difference between the Stokes theorem that I have written here and the Stokes theorem that I have written down here, the Green's theorem in the vector form. You observe that in the Green's theorem in the vector form, we do not use a surface, but we take a domain on R2 and work on R2, but here we are on R3. So, in R3 we are talking about a surface integral being related to a line integral, where the line integral, the curve along which we move now is in the is outlining the surface, it is we are moving along the surface. So, for example, let us understand what do I mean. Suppose I have a surface like this, okay. This is my S. Now, I need to understand what I mean by an orientation of S. So, this is my del S, this is the boundary, these lines are the boundary. So, this is my del S, boundary of S. So, when I am taking the line integral, how do I traverse that boundary? That is also an important question. How do I traverse that boundary? This question is very important and needs to be answered before we can get on to the hang of Stokes theorem. So, if you look at this very carefully, you would realize it is the same game that we are going to play, that when you walk along this boundary, the surface, so if there is a man who is walking along this boundary, then the surface should be always on its left hand side. So, if I am walking along the boundary, my surface, okay, I am on the hilltop, but I am walking along the boundary, but my surface should always remain on the left hand side. That is the very crucial thing. That is the kind of orientation we are talking about when we are evaluating this integral, and that has to be kept in mind. You cannot just throw that kind of thing away. Okay. The book does an interesting job in the sense that it gives you a proof of Stokes theorem for a surface which has been given by a graph, but you can also parameterize the surface, and you can talk about parameters where for two different x's do not go to the same y kind of thing, and which do not surfaces which do not overlap. For those kind of surfaces you can also prove the thing. So, we shall follow the book, because I am sure that many people have already got the book, maybe from LibGen or somewhere from the net, and maybe following the book. So, but you need a teacher, because you also need things to be explained, because everything may not be clear to you immediately. So, before we go and do anything, certain things have to be made clear before I move to actually proving Stokes theorem. So, the program of learning Stokes theorem is the follows. In the first part we do the proof. You might get bored and think that, oh, this guy is a math guy, he simply wants to prove the stuff. Actually, Stokes never proved the Stokes theorem, it was already, the idea was known to Lord Kelvin, and if you, Stokes just got it in a letter from him, and later on he gave it an exam. That is what the book tells. I agree that I am yet to really figure out the history, but I think I need to figure out the history of what's really the stuff. But before I move along, certain things have to be made clear. So, we consider a surface S which is the graph of z equal to f x y. Now, if I have a vector field f which is given as p of I vector, p x y z, of course, p is a function of x y z, q of j vector and r of k vector, then can I write this surface integral which is same as writing integral s f dot n into ds, n vector into ds, n is a unit normal along the surface area vector, and the question is, can we write this surface integral in terms of can we write this surface integral in terms of P, Q, R and partial derivatives of f. This will actually go in long way in handling our situation. The first thing to realize that ds is very easily computed by using a parameterization. So, we have to now talk about a parameterization phi for the graph which you already know. So, whatever be the domain D does not matter, and to R3, that is the parameterization. So, but if you have a graph of a function z equal to fxy, and the parameterization is given as x equal to u, y equal to v, and z equal to fuv is equal to fxy. So, this is the parameterization. Which means here if z is a function of xy over whole of R2, it does not matter, D could be some domain or whole of R2, then phi, this vector phi uv is actually ui vector, vj vector and fuv k vector, but you can replace always u, v and all these stuffs by xy. So, again just for your practice, I am doing phi of u, which is 1 into I vector plus 0 into j vector plus del f del u into k vector, and similarly phi of v is 0 into I vector plus 1 into j vector plus del f del v into k vector. Okay. So, we have already been studying this fact that d of s vector is phi of u cross phi of v into du dv. This is the area differential, right. Actually I should write it, say area vector differential of the area. Of surface area of S. Now, in this particular case, what is it? What is my phi u cross phi v? If I do it, so that turns out to be minus del f del u I vector minus del f del v j vector plus 1 into k vector into del u del v. But if you look into this very carefully, I can replace u with x. So, I can write minus del f del x I vector minus del f del y j vector. I would ask you to actually compute this cross product, which you can do, plus 1 into k vector into del u del v can also be written as del x del y, because u is x. So, ds vector is this. So, now what is my f dot ds? This is nothing but p I vector q j vector plus Rk vector dot product of minus del f del x I vector minus del f del y j vector minus plus 1 into k vector dx dy. So, this gives me minus p of del f del x I del f del x minus q of, we are doing the inner product now between these two, del f this vector and this vector, and this is just a scalar multiplied with it, the differential of the area on the xy plane. Del f del y plus r dx dy. So, integral f dot ds, the surface integral over S, can be written as integral over some domain D, which I have said whatever be the domain, could be R2 also, but okay, let us take some domain, minus P of del f del x minus Q of del f del y plus R dx dy. Okay. So, this is what we have. So, if you want to progress at all trying to prove Stokes theorem, this idea should be in our minds. Now, here in our story, my vector field is not given by any function f written as p, q, r, but in terms of the curl. So, suppose now I have f vector which is given as f1 I vector. So, f is a function from R3 to R3, f2 j vector and f3 k vector. So, f, just if I take f is a function from R3 to R3. See, when I write in a function mode, then I do not put an arrow. So, when you say f is a R3 to R3, it is assumed it is called to be a vector function. But when I write in the IJK mode, in the that kind of mode, then the physicist mode I would say, then I will put an arrow. And I am putting here, you may or may not put arrow, that is up to you, it does not matter, but here you need to put an arrow to say that okay, product of two vectors. So, now our vector field f here is curl of f. Okay. So, I am now going to write down what do I mean by this. Assuming that my surface area, a surface is given by the graph of a function. So, I am trying to see whether I can establish the Stokes identity, Stokes equality through for that particular case. A harder case I leave it to you. You have to understand the teachers, and I am becoming pretty old. So, not very old, 50 years will be soon 51. So, I am taking the hard work off me, you are young guys and girls, and you should be able to do the hard work. I am sorry for telling this, but I am doing quite a bit of hard work, I am sure you would agree to that. So, now if I look into this, I know what I have done, my P is this, my Q is minus of this, my R is this. So, this I will go by this story what I have just written down here, integral of d, my P is this one. So, I will just mark with the chalk that this is my P. When I take curl of f, when I write it as a vector field, this is my P and this is my Q, the Q is minus of this. So, this is your Q, this whole thing, and this is my R. So, what I have is so if I want to write plus Q, Q would be del f on del z minus del f3 del x, you can write it like this. So, P can be written as Q is minus of this. So, So, again now I am writing down. So, instead of just f as PQR, I am writing down what is P in my case of curl when f is given as f1, f2, f3. Now, so I will write down the first P component del f3 del f3 del y minus del f2 del z. Now, del f del x, instead of del f del x I will write del z del x, because we will soon have to apply the chain rule, and because I just want to tell you that you see what would happen here is that f1, f2 and f3 all are functions of x, y, z to r. So, just to maintain that kind of symmetry and uniformity, now I will, instead of f I will use z. So, I will have minus del z del x plus, so here q is minus of this, so del f1 del z minus del f3 del x. So, del f1 del z minus del f3 del x into minus of del f del y, not del f del y, del z del y. F is z actually. Z itself is a function of x y. So, f is a function of x y and z is itself a function of x y. That is where the chain rule issue would come, plus r. So, r is what? R is this one, del f2 del x minus del f1 del y plus so del x minus del f1 del y. Close the brackets, dx dy. That is what we have reduced this whole thing to. Now, this S that we had drawn is here, if you look at it, is related to a domain D on the 2D plane. Could be some domain like this. Now, how in this D, how is D oriented? How am I moving along D? D is, again, whenever we are writing anything conventionally, we will always take it is positively oriented, as we have done in the case of Green's theorem. Positively oriented means if I walk along the boundary of D, so this is my D and this is my del of D boundary. So, if I walk along the boundary of D, as I have already shown you, my area should, so if I am walking along it, my area should always be on my left hand. So, this is something you have to keep on repeating to yourself when you are working with these kind of things. Those who read differential geometry in the future, these things would become very, very useful. So, now here we will come to del D and we will soon see that we will convert, we will now try to do something. We have now written down what is the thing for curl of f, it is written here. So, it is done. I have computed this side of Stokes theorem. Now, I will start computing this side of Stokes theorem. What I would do here is to apply the Green's theorem. In Green's theorem, if I convert the line integral over the line that is circulating around the boundary of the surface, line integral over the boundary of the surface by the Green's integral can be brought up into the line integral over the boundary of the domain, and that is what I am now trying to do. So, My next step is I will parameterize this domain del D, the boundary of the domain del D. That is the first step that now I am trying to compute this. Please understand, I am trying to compute this now, and I am going to show that when I compute this, apply Green's theorem here, I will add this and this would become equal, whatever I had here, whatever I had. So that will come to chain rule. So here parameterization would become important. So let take T between B and A, and let, so here the points are x, y on this curve, right, this. So and let x t, y t be a parameterization of del D. Then Ct, where at Ct is xt, yt, using that parameterization that we have learned of phi, and f of xt yt, then this becomes a parameterization in terms of t of del s. Then Ct is a parameterization of del s. So del s is this one, the boundary of the surface, not the boundary of the domain, is a parameterization of del s. Now let me look at this quantity itself. Here S is the arc length on del S. And ds here is dx I vector, ds dy j vector, dz k vector. Here ds you have to understand, I am not going to compute, and in the bracket I am just writing that here I am in arc length in 3 dimension is basically dr, dx I vector, dy j vector plus dz k vector, because this is the change in the radius vectors, but basically a change here, because ds simply represents this small change here. So this is represented as ds. So here basically difference between the two radius vectors, and that when the difference between the two radius vectors is very small, this difference is very small, dr is very small, then ds and dr are almost nearly the same. So that is ds is taken to be dr. The straight line very well approximates that curve. So now I can now write ds, and I can just do a, now instead of writing del s, I can write through a parameterization in this form, f1 dx dt plus f2. So ds I write as, now this can be written as ds dt dt. So and dx dt I vector, dy dt j vector, dz dt k vector, and so I can write that thing here in this form of once I do the dot product you know how to do it. So it's you can say, oh, is it really dot product, these are really numbers, yeah, very small numbers, so we are doing those simple dot products. This is a vector actually. Now, if I go by the chain rule, del z dt is equal to del f dt is equal to del f del x, x is just one variable with respect to t. So, it is dx dt plus del f del y dy dt. This is by chain rule. Now, once you know this, so you put it here, put dz dt here and then integral ds. Now, I will do the manipulations, you check the manipulation, but I am just writing it down. It is very simple, it is you do not even, you can just do it without just by observing this. So, you will f1 with dz dt, will f3 you will have this one. So, with dx dt you will have to combine this part. So, if there will be f3 multiplied here. So, let us see what happened. So, dz dt is now del f del x dx dt plus del f del y dy dt. So, f3 gets multiplied into two parts and then they are combined up with the f1 and f2. So, f1 plus f3 del f del x. So, this can be written as del z del x dx dt, f is z actually, del z del y dy dt. So, del f del x, sorry, del f3 del z del x dx dt is now common, it can be taken out. Dx dt plus f2 plus f3 del z del y dx dy dt. Now, this should ring a bell immediately in your mind, because now I can take the integral separately, but what would be this? This is now by, if I now I can write them again back as a, I can take the t off by multiplying these two and write it as if I am doing a line integral on the domain del d, because now I am in two variables case x and y, I am in the two variable domain. I no longer have, so I can now look at this whole thing as a function p and q, like I, or the one I did for Green's theorem. So, it is the function f pi plus qz. So, basically this is now written as f1 plus f3 del z del x dx plus f2 plus f3 del z del y dz. So, this is the form of the Green's theorem, p dx plus q sorry not dz dy, p dx plus q dy. This is the form of the Green's theorem. So, now we have to apply the Green's theorem. So, let me just again write it down. So, let me write down the Green's theorem. So, by Green's theorem, integral del d f1 plus f3 del z del x, which is p dx plus f2 plus f3 del z del x dy. This is equal to integral over the domain itself, right. So, in 2 dimension your domain is the surface, is a double integral. Now, we are converting this, computing this line integral in terms of this double integral over the domain of, this is my q, so this is my p in the Green's theorem, this is my q in the Green's theorem. So, del q del x, so del x of f2 plus f3 del z del y minus del p del y del y of f1 plus f3 del z del x, z itself is a function of xy and everything f1, f2, f3 is a function of xy, z, please understand that. So, chain rule is now required to make an into dx dy, chain rule is now required to make any further progress. So, applying chain rule, let me see how applying chain rule. Please understand that there is a product also here. So, we have to apply the product rule also. While applying the chain rule, do not forget to apply the product rule. So, let us now integral d. So, this whole thing is now integral d. Let us see how do I apply one chain rule and then another. First look into this. So, all of these thing is in terms of x, y, z, right. So, I can first separate it out, del x of, so here is the function of x, y, z. So, I will write it in terms of a chain rule. So, I will do for f2 and then I will write it out, but remember my parameterization here and you have to understand z, these f2s are functions of xy, f1, f2, f3 are functions of xy, z and z is a function of xy. So, you have to do, when you write del x of f2, you really have to do the chain rule, right. So, if I apply the chain rule here, so first I will do del x of f2, del x which is 1 plus del f2 of del y plus del y del x, because I am doing it with respect to x. So, del f2 of del x into del x. So, I first separated this f2 and then I am doing separately this one. So, I will have here, I am just writing it and then I will rewrite freshly, is del x del f2 of del y del x. So, if I write the chain rule for f2 with respect to x, then this will be the chain rule, because z is a function of xy. Please understand, here z is a function of xy and that is why I have to write down this whole, chain rule. So, del f2 del x is coming through this way. You may do it like this, or there is another method of doing it. I think I will try to make it much more simpler for you. So, when I am computing this part, I am computing this part plus this part. So, del x of f2 plus f3 del z del y into del x plus del y of f2 plus f3 del z del y. So, this is respect to x, del y del x. So, this whole chain rule is with respect to x. So, I am just doing this, knowing that z is connected through fxy, x is x, y is y, but z is connected through x and y. So, basically I am doing the uv thing, this is in terms of uv basically, but okay, u is x and v is y. So, now I will have del z of F2 plus F3 del Z del Y into del Z del X. This thing minus the same story I can write in terms of Y, del Y of F1 plus F3 del Z del X this is in terms of Y now. So, del Y del Y sorry del Y del X plus del Y of F1 plus no I am making a mistake, it should be F1 plus F3 del Z del X, F1 plus F3 del Z del X, no it is right, into del Y plus del Z of F1 plus F3 del Z del X. Actually, you can write everything in terms of UV, and then put del Z X instead of U and V instead of Y, and Z as Z F. Into del Z del Y. So, this is the chain rule, because you have to take into account that Z is a function of x y. So, this is what I have written. How does this is into dx dy. So, how does this expression pan out? Let me write it down. Let us write it down, this expression. So, del x of f2 del f2 del x into del x del x. So, I have del f2 del x plus del x of f3 into del z del y into del x del x. So, it is 1 plus this part del y del x is 0, y is not represented by x, y and x are independent of each other. So, now it remains del z. So, del z del f2 into del z del x as del z of f3 del z del y del z del x. Now, you have to apply in this cases some cases product rule minus. So, here in this case del y del x, this part is 0, it goes away. So, the first part becomes del f1 del y plus del y of f3 del z del x plus finally, this one becomes del f1 del z del y plus del z of f3 del z del x into del z del y. Now, I will expect that you should be able to write the chain the product rule here. You have to write product rule here, you have to write the product rule in this case del x of f3 del z del y, del z of f3 del z del y, del y of f3 del z del x, del z of f3 del z del x. So, if I write down that product rule, then so finally my integral del s f dot del s will take an interesting thing. So, if I write down that whole thing, so it will become del f2 del x plus del f2 del z del x, del f2 del z into del z del x plus del F3 del x. So, here you have to see. So, here it will be del F3 del x del z del y plus F3 into del 2z del x del y. So, that I will put in the end, the second order thing, into del z del y. The second order, there is another second order term will come here, we will put it at the end, and we will do the other things, and I am just rearranging this thing, del F3 del z del z del x del z del y plus F3 del 2z del x del y. Here what would happen, del z of F3 del z del y. So, here if I look at it carefully, del F3 del x into del z del y, del F3 del x into del z del y, which also come here, del F3 del x into del z del y. So, del F3 del z into del z del y into del z del x, and you also have to do, so del 2z del z del y, when you do del z del y, and then if you take del, so here you will have del F3 del z del y plus F3 into del 2z del z del y. So, del 2z del z del y is 0, right, that z is a function of x y. So, you write this part minus, I will just write it in a fast way, del F1 del y plus del F1 del z del y plus, I am running out of time, del F3 del y del z del x plus del F3 del z del y del z del x plus F3 into del 2z del y del x into dx dy. You know, if you rearrange this whole thing, you know what you will get? You will get back what we got. If you rearrange this whole thing, you will get back this. If you rearrange what we wrote at the end, you will get back this. That is the whole key. So, this is nothing but S into this curl F into ds, and voila, we have proved the Stokes theorem, and that is the end. We have proved the Stokes theorem, and that is the end. So, I wrote something very fast because I expect you to do it, because I explained you how the chain rule is working, but we have proved, if you do this computation, if you check it out, because you see the second order term will cancel, this term will cancel with this term. So, we will be left with first order terms, and if I go back to this, you will exactly get back this, because this d is equal to S, and that is it, and we have proved the Stokes theorem, voila, as the French would say. In the next class, we are going to talk about the examples of Stokes theorem. So, we have exceeded our time quite high. Okay, does not matter, we will go along a bit. Thank you. Maybe we will not do the proof of the Stokes Gauss's theorem, but so if we have got 1 hour, another 40 minutes, so we will go for a single full class. Today we will have 3 classes, 1 and 2, and there will be a single full class tomorrow, and that will be the end. And I hope, because there is no use breaking up things, now we will do the problems for Stokes theorem. It is very important to know at least one proof. Thank you.